Here's a rather tricky fluid mechanics question that explores that classical fluid mechanics problem regarding to an ice cube melting into a glass of water. So if you know the answer to that question, give this one a go. I think it's going to challenge you a bit. And if you want to do it, you can pause the video now and try it yourself. Otherwise, I'll just continue with it. And if you'd like to see anything similar to this on the channel, or if you have any suggestions for any specific problems you'd like to see, let me know in the comments. So here's what we have. We're dealing with a piece of ice, and the difference compared to the original question is that this ice cube is tied with the help of a thread to the bottom of a cylindrical container, okay, which has some amount of water. We don't really know or care how much water we're dealing with. And we know that the length of the thread is adjusted so that the ice is not fully submerged. So there is a part of the ice which is still above the water surface. And we also know that the tension in the string is 1 Newton. So the question is the same as with that original fluid mechanics question, which is what happens to the water level when the ice melts? So the difference is that now we have a thread which is in tension, and we have to figure out what happens when there's no ice, and obviously there won't be any more tension either because that thread won't be attached to anything. And we're given a couple of numbers. So we know that the area of the bottom of the vessel, so A, B, let's say, is, or let's just call it A, I think that makes more sense, is 400 centimeters squared. And as usual, I would just convert those to meters squared. So that's 0.04 meters squared. We know the density of the water as well as 1000 kilograms per meters cubed. They give it to us in 1 gram per centimeter cubed, but I would recommend converting that. And then the density of ice is slightly less than that of the water, and it's 900 kg per meters cubed. Right. So what happens to the water level when the ice melts? And this is a multiple choice question, so you have a couple of options available. So does the water level go up? Does it go down? And you have two different values for up and two different values for down. Okay. Again, if you want to try this yourself, feel free. Otherwise, I'll just continue with it. So the first thing I would do is draw a free body diagram of the ice. So I'll draw a free body diagram of the ice while it's being attached to the string, and the free body diagram looks like this. So this is the ice, and then we have the forces acting on the ice. So we have weight, which is pushing down. We have the tension in the string. That's the difference. Okay, so in the original question, you don't have this this force here because the ice wasn't attached to anything. So you have weight, you have tension, and you also have that upthrust. So let's say if the ice is floating above this, well, if this is the water level, if that's a free surface, then we have a buoyant force as well, which is FB, which is the density of the water times the displaced volume times G. So this is what we care about. And we're trying to find an expression for that displaced volume. And the plan here is we want to make this the subject. So we want to find an expression for the displaced volume before the melting phase, and we want to find a second expression for the displaced volume after the ice has melted. So let's start with a free body diagram of the ice, and let's try to get what this is first. So here's what we have. If we write Newton's second law for this scenario, we can see that everything is in equilibrium, so all the forces balance each other out, right? So we have the buoyant force, which is the only force acting upwards. So that's rho W times the displaced volume times G. That equals the forces acting downward. So that's going to be equal to tension plus mg, basically. Okay. So because it's this we're interested in, I am going to extract that from here. So the displaced volume is T plus mg over rho water times G. And if you want, you can actually split the fraction into. I'll do that because it's going to become simpler later. And that's going to be plus m over rho W. And that's it. So this is a displaced volume. Let's call this the displaced volume 1. So that's the displaced volume of the water while the ice is in the tank, right? Before the ice melts. So we don't really know everything here because we don't know how much, we don't know how heavy the ice is. So in other words, we don't know this M, right? We know the density of the water, we know the tension, so we cannot actually get an expression, a direct expression of this displaced volume. But the question isn't even asking for that. The question is asking for the change in displaced volume, or the change in height between, before and after the melting. So let's consider what happens after the ice melts. So what happens to this displaced volume, which we're going to call in this case VD2? So how much water is going to get displaced once the ice melts? And to do that, here's how we're going to proceed. We're going to say that the ice has a mass m. Okay? So when this gets converted into water, or when it melts, right, the amount of resulting water, the mass of the resulting water, is the same, right? Because if you start with, let's say, 10 grams of ice, 10 grams of ice, and those 10 grams of ice melt, then you will end up with 10 grams of water, right? You're not going to just end up with more water or less water out of nowhere. So there's this idea of mass conservation that you have to be aware of, okay? So in other words, we start with an unknown amount of ice m, and that's the same mass of water that results after the melting phase takes place, okay? So the displaced volume is therefore going to be the volume of the resulting water, after the melting takes place, obviously. Okay, and what's the volume of the resulting water? Well, it's the mass of the water, which is the same as the mass of the ice, over the density of the water. So it's this. Okay, so after the ice melts, the amount of displaced volume, which is the volume of the melted ice, which is the volume of the resulting water, is m over rho W. And that's the displaced volume in the second scenario. So now we can find what the question wanted us to do, which is the change in height. But we'll first find the change in volume, and then we'll correlate that with the change in height. So the change in volume is going to be the final displaced volume minus the initial displaced volume. And we know the final displaced volume is m over rho W, and the initial displaced volume was this. Okay, so we have T over rho WG, and then plus m over rho W. And you should notice that this and this cancel out, and we're going to end up with a change in volume of minus T over rho WG. So this actually means, the fact that we have a minus here, it means that the volume decreases. Okay, so the volume decreases. And if the volume decreases, it means the water level in the tank actually goes down. So we can go back to the question and we can realize that the correct answers are, well, the correct answer is either B or D. Okay, because there's going to be less volume of water after the ice melts. And now we just have to find out how much. Is it 2.5 or 2.8 times 10 to the minus 3 meters. So to do that, we will first find the volume. So the volume, the change in volume is minus 1 over the density of the water is 1,000, and G is going to be, well, let's just use 9.81. So from here, the change in height, because it's a cylindrical vessel, it means the change in height is the change in volume divided by the area, which is this. Okay, so we have the change in height is this over that area. So let's write it here actually. So we have minus, and then we have 1 over 1,000 times 9.81, and this is multiplied with the area that is 0.04. 0.04. Everything is in SI units. So let's see how much we get. So it's 1,000 times 9.81 times 0.04. So I'm getting, yeah, so this is minus 2.54 times 10 to the minus 3 meters. Again, the minus tells you that the water level goes down, right? So it goes down by this much, 2.54 times 10 to the minus 3 meters, which means that the closest answer to that is B. The reason they got 2.5, I'm assuming it's because they used a G of 10 meters per second squared. Okay, but yeah, so that's how you do the question. You look at what happens before the melting phase, you look at what happens after the ice melts, you compare the two displaced volumes, and that helps you figure out what happened to the water level, if it increased, if it decreased, and then divide by area and you get the height. And that's the end of the question.